Here we go, PFC and fish. We got to start with the cartoon. I was giving a course at the University of Laval in Quebec City some years ago, and I start talking about fish, and this guy at the back of the room suddenly like jumps up and runs out. And I'm like, guy must have driven him away, huh? And he comes back about 2 minutes later, and he's holding this cartoon in his hand that he had taped onto his door. So I thought that's kind of appropriate. Um, Fish, what is it? Where does the name come from? ITASCA, one of its early codes, continuum codes, was called FLAC, Fast Lagrangian Analysis of Continua, FLAC. And so Peter Cundall designed this language that was a way of people. Okay, so we created FLAC and started selling it a long time ago, and people then would come back and say, oh, this is great, but I want you to like add a plot item. I want to get the second invariant of the stress tensor. So they'd go and they'd add that to the code. And then someone would come back and I want to get the third invariant, and I want to get this, and I want to get that. And it was like, geez, it might be easier to just make a simple language that would allow people to gain access to what's going on inside the program. And so that was this language. And the idea was, well, like if you're in Finland, you speak Finnish. If you're in Sweden, you speak Swedish. So if you're in the world of FLAC, you speak Flackish. That was the original name of this language, which then became shortened to fish. It's now part of all ITASCA codes, and it's slowly grown. Peter did just originally all that you could do was like gain access to certain data in the program. And then he said, well, geez, if I made functions, that would make it much more powerful. And well, if I had a couple controlling looping constructs in there, and what if we could save memory? All kinds of different things started getting added to this. And at this point, it's become a full-blown programming language, comparable to Python in many ways. It's sort of like C++ and Python all rolled into one. It's a full programming language. You can do anything you can program in fish. So it's as powerful as C++ or Python. And so we're going to find out that we use this quite extensively when we work with PFC, because usually we have to write our own specialized functions to do things that we want to do. If you were only building boxes and putting in particles and letting them pile up and watching them flow out of them, you really probably wouldn't need much fish. But if you're going to try to now, make an assembly, get it bonded together, give it special properties, perform a triaxial test on it, you're going to need to do specialized stuff. And so you're going to need to work with fish. Okay. So what is fish? In the world of fish, it's a programming language. So we have this idea of functions, right? A function has a name, it takes in parameters, and it does something, and you can tell it to be executed. That's the idea of a function. The way that this is going to work is you're going to create these functions and you're going to enter them by means of a data file, okay? And when the function gets read in the data file, what actually happens is that it gets internally compiled into a list of instructions, and that gets stored in PFC's memory space. Okay. Functions, of course, can have parameters, right, that you pass into them. There is an idea of variables. All variables are global, meaning that they're accessible from everywhere. Okay. Although you can have local variables within functions, okay? Local variables are basically hidden. They only exist inside that function. They're not accessible to the rest of the world. Variables are what we call dynamically typed. They can be things like, and you can have a variable called Fred, and at some point you can say Fred equals 3, at which point Fred will have the value of an integer, which is 3, but then later on you can say Fred equals the string hello, and now suddenly Fred is equal to a string. It's a type string, okay? Or Fred can be 26.3. Now it's a floating point number, etc. And there's a very rich set of different data types that are available. Things like vectors, which are 2D, 3D sets of it's like a vector, like a 2D vector is two floating point numbers, X and a Y coordinate, right? There's matrices, there's arrays, there's lists, etc. One of the powers of Fish is that it's integrated with the codes. So there are then built-in functions that allow you to get access to information about the model. So for example, there's a function called ball.density, and this is what's called a pointer to a ball. Which ball do you want to get its density of? And so you could use that to do things with that density, to get the density, to set the density. Here's one that gives you the position of a particular contact, right? Okay. And then there's all the different math functions that you would expect: square root, cosine, sine, etc. Things like that. Then another thing is often we have to do things like we need to traverse the list and do something of every single ball in the model, or we need to visit all the contacts and do something. So there is this looping for each construct here. So this statement is basically saying doing a loop over all balls in the model. So that's going to visit all balls in the model and you can do something with them. Okay. Everything related to Fish is what we call part of the model state information, which means that when you save a model, when you come back later and restore it, all the Fish information is still there as well. Okay. Now let's go through some examples to try to make this make more sense. So let's say that we wanted to create a system like this of 4 walls, okay? And we're going to parameterize this thing. It's got a width and it's got a height, okay? So one of the ways we could use Fish is to do that. So what we have here is this would be inside a data file. And so inside the data file, we come to this. Oh, this is a global variable called width, and we're going to set it equal to 1. And here's another global variable called height, and we're going to set it equal to 2. And then eventually we can give in our data file, right? We've done this kind of stuff. Wall generate command. We give it the name of the wall, and we're going to use the box keyword. And that box needs to know the X min and the X max and the Y min and the Y max. So notice with these square brackets, that means evaluate the Fish stuff. So this is going to go right. We want, if this is my coordinate system, I want to go 1/2 in the negative direction, 1/2 W, and in the positive direction of X, 1/2 W. And then these is that's X min, X max, Y min, and Y max, right? So you could have a data file, and at the very top, you just specify width and height, and then every time you run it, it's going to, create what you want. So we've parameterized a model. We do this all the time. What we call material modeling support package, which is what we're used to create bonded materials and to do tests on them, is essentially a big, huge parameterization thing, where essentially you're just going to be setting these variables at the top of a data file, and then you're going to be running it, and it's going to use those internally to do what it needs to do. Another thing you might do with Fish is effectively make a whole new PFC command. So let's talk about that. Let's say that we want to make a command, and so what we have to do is make a function. And so we'll make the command we're going to do is give the name of the function make circular hole. Okay. And so before we can do the function, we got to do a little mathematics here. Okay. Because what the function is going to do is it's going to go through every single ball in the model, and it's going to make the test to determine if the ball is inside the hole or outside the hole. And if it's inside the hole, it's going to delete it. If it's outside the hole, it's going to let it stay. Okay. So, we work out the math here, right? So here's our circle is defined by a center and a radius. So those will be input parameters to the function, make circular hole of this radius at this center, right? And then as we loop through, right, if this is the point of the center of a ball and this is the center of our circle, we can define these 3 floating point numbers, right? This is the X component of the position P. This is the X component of the center, right? So this is delta X, A is delta X, B is delta Y. As you know, Pythagoras told us that they're related in this way. and then we're going to make that check, right? If it's less than R, then we're going to delete it. And this is our little example. So if we look at that function, so here's our mathematics we need to know. So here's what this is going to look like inside of fish. Okay, so here's our function. This is a function with two parameters. The function, so we say fish define, it defines a new fish function. We say fish define function name, blah, 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 end. So this is one thing that says define the function. This is the inside of the function. When it gets to here, it says done, the function has been defined. After the function has been defined, somewhere later on, anywhere later on in PFC, because once this gets defined, it exists inside of PFC's memory space. So that function is now available to be called. And so we're going to call it inside of a data file by using these square brackets. Basically, what happens is anything inside the square brackets is going to be treated like the world of fish. And so what this then is doing is here I'm actually calling the function. So I'd say make circular hole, and it has two parameters, the center and the radius. Well, the center, for my example here, is going to be 1, 1, because this is 0, 0, this is 2, 2. So the center is going to be 1, 1. So that's a vector. So I'm going to say vector 1, 1. That's what the center expects to be. The radius is just a floating point number, 0.5. Okay. Now let's unpack the internals of this function. So this is this loop for each construct, loop, blah, 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 end loop. So what are you doing? This is saying loop for each, this BP thing is going to be a pointer to a ball, and I'm going to be able to use it inside the loop to do stuff. And so I have to say for each BP and that are in this ball.list, this is a function that is an embedded PFC thing, and it will give you the list of all the balls. Inside of PFC, we're always maintaining a list of all the balls in the model. So this is going to basically loop over all the balls. It's going to create a local variable called BP, which we can use inside here. So how are we going to use it? In addition, we're going to make local variables A, B, and D. Remember, that's what we needed to compute, A, B, and D. So how are we going to get those values? Local A. So remember A, it's the position of the ball, the X component of the position minus the X component of the center. So this ball.post is a built-in fish function that gives you the current position of a ball. Which ball? This ball BP. You need to tell it which ball. And remember BP, we're looping over all the balls. So each time you go through the loop, BP will be a pointer to a different ball. And so this is just the syntax. BP, this is the position of ball. This is the arrow X component of the position. And this is the X component of the center. Center was a parameter that got passed in. Okay. We do the same thing for the Y, the delta Y, and then we call that A and B, just like in this picture, right? Now we need to compute using Pythagoras's theorem. So now we can operate on that. So this is the way of saying squared. I could have said A star A as well. So this is A squared plus B squared. Feed that into a math function. This is going to return the square root of whatever is in here, right? So that's going to get returned, and that's going to be a local variable that's only accessible inside the function called D. And then we're going to check, right? Is D less than the radius? That's again, the radius was the parameter you passed in. If it's less than radius, we're going to call, well, that conditional, right? If less than this, we call that a conditional in programming. Then we're going to call another function called ball delete. Which ball do I delete? The BP one, the one that's currently pointed to. Okay, so this is the idea of fish. We just defined a function. Function has parameters, and then later on, at some point, we can call the function. So there we go. Make circular hole. Vector 1, 1.5. Boom. And when we do that, it's going to go through and do this, and it's going to delete those particles. All right. Now I can't see my full screen when I have it in full screen mode. I need to see this. So let's look at this, create new command. So in the PFC and fish directory at the top, here's this PFC and fish project. So I'm going to open it up. The first thing it's going to do is make a simple little packing, my first pack. This is just like the thing we've already been talking about. It does the generate command. There's overlaps of particles. We let them squeeze, come to equilibrium, and there's my system. And we're going to save this as a save file called TightPack. Notice, blah, 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 model save TightPack. So we've done that. Now we're going to look at this create new command example. So what's this going to do? There it is. Return. This is the function we just went through. So notice this is a data file. So what's it going to do? When I execute this data file, it's going to restore the TightPack system. It's going to create this fish function. So let's just do that. Okay. And I can say over here, oh, look at this. This is my fish symbol editor. At this point, there's one function. It's a function that takes two parameters, F2. And that's what's inside of PFC's memory space. All right. Then I can do this. So let's actually execute it. Forget about this. Let's just execute it. So I'm going to say make circular hole, and I need to put it in those square brackets so it knows now that this is not a command. It's not a built-in PFC command. It's a special fish thing. So I'm going to say make circular hole, and I needed to give it a center and a radius. So the center is going to be at 1, 1, comma, the radius is 0.5. End of the square brackets, boom. So let's look at this. There, run it. I just deleted those particles, right? Go back to this. Let's not worry about this other function. We're going to talk about that on the next slide. But here's the idea. There's the same thing I just did. So create this function, and now I can execute the function. So if I change this to 0.7 and I run it again, of course, it's going to be 0.7, right? Okay. So you can see right there, I've effectively created a whole new command. It's called make circular hole. Okay. Now the other thing you can do is you can, inside of a fish function, you can send commands to PFC. Okay. So I could, if I want to delete the particles in an area of a circle, there's a command that I already could use, ball delete. And then I would say range circle, center radius, right? So I could just give that command and it would delete the things. So what I can do when I make my function, so I'm going to make a new function called make circular hole 2. And instead of having to loop through, like I did here, loop through all the balls and make this check, well, for this particular functionality, there already is a command to do that. So I can just invoke that command. So this has to be enclosed in a command end command construct. And then anything so when I execute this function, anything inside this command end command gets sent at that time to the PFC command genie. And notice when I send it the command, I say, oh, I need to give you the center. Oh yeah, in brackets, this is the center because that's the variable I passed in. And this is the radius. That's the variable I passed in. Okay. And so then I would invoke that by giving the name of that function, make circular hole 2. Again, passing it in the same parameters, and I should get the same result. So that would be here. I will comment out this, make circular hole 2 for the 0.5. And now I just did the same thing. We talked about parameterizing a model, right? That's a use of fish. We do that all the time. We talked about creating a function to effectively give you a whole new command. Do this thing, right? internal to functions, we can actually send commands to PFC. So when we execute the functions, those commands get executed, okay? Now, watch this. We can perform a parameter study, okay? So what do we want to do for this example? We want to basically say, I want to have 3 different values of density and in this pile of sand. And so I'm going to set the density to 10,000 and I'm going to run it to equilibrium. And then I'm going to set it to 15, 20. Okay, let's just run this first. So it's called parameter study. Let's just do this first. Okay. So I'm going to restore the tight pack. Remember, tight pack.save. That's the tight pack. I'm going to restore that. And what I want to do is I want to remove the remove some balls on the top and turn on gravity and let that thing settle. So what I just want to do is this, so that this is clear. Just getting things set up. I just deleted particles on the top, and then I hit continue, and I want to get to equilibrium because we're going to now start to play with this example. Okay. So now that's just solving to the ratio 1e minus 5. So this part should make sense, right? Restore it, give it a new title, delete the balls near the top, turn on gravity, cycle until a convergence ratio is reached, and save it. So I'm going to call that sand pile. Okay. Now, after that, forget about this. Don't worry about this. I want to run this thing. Let me just run the whole thing. Watch. Now it's coming to equilibrium. Okay. It says sand pile of balls in a box with gravity loading, initial state. Now we're done. Set the density 10,000. I set the density to 10,000 and this is my system. Now watch, when I say continue, I'm going to set the density to 15,000. Watch. It sinks further. Now I'm going to set the density to 20,000. Sinks even further. So let's look at how we did that. Okay. Here's what we're doing. Let's just unpack this. We're creating a function called run cases. And then after we create the function, we're going to call the function. Okay. There's going to be 3 cases to consider that have 3 different densities. So what we're going to do is we're going to create there's a concept of a list. What's a list? A list is a collection of variables that you can access one by one by one by one. That's the idea of a computer program. It's the idea of a list. Okay, so here, this is actually creating a list of 3 floating point numbers, and it's assigning it to a global variable called myDens. It's like my variable name, my density. Okay. Eventually, inside of here, we're going to execute a command which is going to set the ball densities to, and this is, notice it's a list, so I have to say which element of the list. Element 1, element 2, or element 3. So that's what this I is. Where the heck does I come from? When I execute the function, this is a looping construct. It's gonna make a local variable called I, and it's gonna set it to 1, and it's gonna do this loop until I is equal to whatever this num cases is. Okay, in our case, we're gonna pass this in as 3. So num cases is 3. So this is gonna go through this loop 3 times. The first time through I is 1, the next time through I is 2, and then I is 3. Okay. Now, to make things even more interesting, the title I'm putting a title on here. Sand pile with ball density of 20,000. I want to see what that is so I can look at that. So here's what I'm doing, right? I'm creating a new variable locally called title new. And notice quotes, and so this will be a string. It's going to be sand pile with ball density of, and then I'm adding to it another string. This is a command that takes this variable. Now this is going to be my density 1, for example, initially. it'll be 10,000, turns it into a string, adds it onto this string. So the end result is this title new is a local variable that's going to actually say sand pile with ball density of 10,000. The next time it'll say density of 15,000. So that's the new title. And so inside, I'm going to issue a command. I'm going to say, remember, it's the model title command. And what's the title? Well, it's expecting a string here. I already created a string, which is my variable, my local variable called title new. So that's going to assign to PFC that title. After it's done solving, we're going to save the model. And so we're going to create save files that are going to be called sand pile. See up here? Save states, sand pile 1, sand pile 2, sand pile 3. How do I do that? I'm going to locally create another string called sand pile plus, now I, first time through, 1, then 2, then 3. So it'll be sand pile 1, 2, 3. And I'm doing the model save command. What am I saving? This is the name of the file. Sand pile 1, sand pile 2. If I'm setting the title, now I'm setting the ball density. Then I'm going to do the model solve to the given ratio average, and then I'm going to save it. And after I'm done saving it, I'm going to pause because I'm sending this to the command processor. So when I execute it, it goes through I = 1, sets things up, solves, saves the file, and then it waits. And when I hit continue, oh, let's continue the loop. Now I go to the next one, I = 2. And I set the density to a bigger value and I continue. And this is this. So if I just change these values, it's going to change, the densities I'm putting in. Great thought has gone into these examples here. Okay, let's just play with this thing, make sure we understand it. So let's get rid of my first pack. I'm just going to close that editor window. Get rid of the create new command. I'm going to close that editor. So we're just looking at this, the system view and the parameter study.p2d data file. Okay, right? So here it is again. So let's just run this thing again. Oh, it's sitting here at continue. So let's run this thing. Boom. I'm just doing that initial thing. There's the first one, and it says ball density of 10,000, and it created a save file, sandpile1.save. Right? Next time through the loop, 15,000, and it made another save file, sandpile2.save. Right? Another time through the loop, density of 20,000, and now it's just sitting there. It's just sitting here paused. So when I hit say continue, it's going to go here. It's going to check. Oh, wait a minute. If I increment I, it's more than 3. So I'm done with the loop, which means I get to here. I'm done with the function. I just finished executing this function. And now I go and I say program return. So that kicks me out of everything. Okay. Now here's a trick. Watch this. Let's go and just change. This is what's driving it, right? This list of these values. So let's change my density. Now let's see if I can get this right. My dense equals list.sequence. Let's do 25,000. And let's do 35,000. And let's do 50,000. And I can only do 3 because I've set this up to it. Well, I can do any I want. Let's just do 3 again. Let's do this. So this actually changed the value of my density. I can say list fish list what? My density. I think this is how you do it. Fish list. Oh, come on. Well, I want to show you what that variable is. Where the heck is that example? I can't remember the word. Fish list contents. That's it. Fish list contents of that thing called, of the variable called my dense. Boom. There. 25,000, 35,000, 50,000. So now I can execute the command function, run cases. There's 3 in there. Boom. Return. There we go. And it's telling me there's 25,000. Continue. It should be 35,000. Did it again. Now it's having a hard time getting equilibrium because these guys are almost pushing out, and it's probably going to push those out of the box with 50,000. Remember, if these guys go past the center, they're going to go out. So I think it's, yeah, well, you get the idea. We're not worried about the physics of this. We're worried about the general idea. Okay. So notice right there. So essentially now by setting my dense, we can, we can do this. We could perform a parameter study very easily now, right? Because we could just go and say, set my dense equal to blah, 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 run cases. And then it's going to make all these save files along the way. Okay. Next one, what else could we do with this? We could define a new history variable, right? There's a small number of built-in histories, right? Like for a ball, you can keep storing its velocity or its displacement or something else. Let's say that what we wanted to do is we wanted to actually measure what is the total weight of all the balls in the model. Okay. And let's say we wanted to do that. And so if we ran this previous thing where we set the density to 10,000, 15,000, 20,000, right? As we do that, for more density, there'll be more total weight, right? And so if we could create a fish history about total weight, this is what it would look like. Weight of all the balls, right? As we do steps. Here's the weight of all the balls. Then we increase the density. Now there's the weight of all the balls. We increase the density. There's the weight. Okay. So this is going to be our function called, we're going to make a function whose goal is to go through all the balls and return the total weight. And then we're going to hook it in right here to the history mechanism. So we're going to say fish history, and the name of the history is going to be called total weight. And now, since it's a fish history, we need to give it the name of the fish function that's supposed to return the value. And so also here, we're setting the interval at which the histories get sampled. By default, histories get sampled every 20 steps. We're going to set it so that histories get sampled every single time step. And so here we're hooking in again, we're creating a new history, but it's a history of a function that we created, of the result returned by that function. And so let's look at this. How do we get this? I'm going to start my little math thing. So we want to get the weight of a ball. Weight of a ball is equal to what? The density of a ball. Whoop. Density times the volume, right? And the volume, what's the volume? T equal to 1 in all of these systems, right? And to get the weight, gravity, right? It's mass times gravity. So this is our mass and that's our gravity. So let's look at what we did. So we're looping over all the balls here, okay? For the particular ball, BP, we're computing its volume. Pi, radius, that's pi r squared times unit thickness. That's that term, that's the volume. The weight then is going to be of the previous weight. We're going to sum the weights. So it's going to be the previous weight plus the density of that ball times the volume times the gravity. We've set the gravity up here, local variable 9.8. We've set weight to be 0. Every time we go through here, we're going to add an increment weight by density volume times G. And when we're done with this loop, we will have visited every ball we will have added its weight. And so therefore this thing called, this local variable called underscore weight is the final weight once we get to here. And so this is how you return a value from a function. You just say return whatever that thing is. So that means when I execute this function, the value that it will return will be the total weight of balls in the model. And so this then, and again, this then is hooking that into the history thing. Okay. So if we look at that, so this one is called parameter study, that P2 dat. So let's, that's the same thing. So there's that function, weight of the balls. That's what I was showing. We're hooking it into the history mechanism like this, right? So if I hit a return here, just have to wait a second because I'm solving that whole sand pile thing. So created history. The history name, the name of the history is total weight. There you go. That's the name of the history. And what's it a history of? It's a history of a fish function called weight balls. I could say history list. There's all the histories in the system. We only have one history. Okay. And so at this point, that's my system. Okay, that's the initial thing. I can now call that function. It's just a function. So weight balls, put it between the square brackets, and I spelled it wrong. Weight balls, boom. It returns to me a value. That's the weight, 24464. Okay. So now, of course, though, I have that in here. Now, when I run through these three cases, the weight should keep changing every time I rerun this to a new thing. So let's do that. System view. So the weight should be a certain number now. Continue. Weight should be bigger at this point. Let's hook in a history and see. So we're going to say plus history chart. Turn off everything else. There's my possible histories. I want the one called total weight. There we go. Let's make this. The y-axis is that total weight. It was a certain value. Now we increased it. Now it's another certain value. Let's just change the y-axis. Let's make the minimum value be 0. There we see, right? Let's make the and so there we go. So now when I hit continue again, because at this point, if I, yeah, this has a density of 15,000. So now when I hit continue again, the density is 20,000, and now it has a higher weight. All right. So going back to this, get rid of that. All right. So when we're doing our biaxial test, for example, we're going to make a function that's going to say sigma y, and that function is going to get hooked into a history variable called sigma y, and then we'll make another one called epsilon y. And so those functions are going to return the axial stress and the axial strain. And then we're going to hook that in as two histories, sigma x and sigma y and epsilon y. And then we're going to plot with the history thing. We're going to plot sigma y versus epsilon y. We'll do this later, but this is the idea. We do this all the time. Typical use of fish. Okay. Here's another one, even a little bit more complicated. So we can set this up so that when some sort of event happens in the program, our function will get called. Okay. And there's certain events that can happen that we can use. These are called callback events. Okay. So while the program is cycling, if one of these possibilities is ball delete. So while the program is cycling, we hook this in. While the program is cycling, if a ball ever gets deleted, our function gets called. Okay. Why would I do this? All kinds of different reasons. You might want to be, maybe you're doing a flow of granular material, and maybe you want to measure the weight or yeah, the number of all balls that are falling below a certain level out of the orifice. And then what you could do is you could be setting it up so that when they fall below an orifice, they get deleted. And then once they get deleted, here you might like have a counter, a global number, how many, and then that how many keeps getting incremented every time. Okay. So here, let's look at how we would do this thing. So we're going to restore the tight pack system. That's our little example. And we're going to have a global variable called my count. And what we're going to do is every time a ball gets deleted, we're going to increment that variable by 1. Okay. And so here's the function, count deletion. Let's not worry about what it does. First, we hook in to this callback mechanism. We call this a callback because that's a computer science term. A typical user interface, you have these buttons, and when you press a button internal to the program, a certain function gets called. So the name of that in the computer science world is a callback. So you set up a bunch of buttons on the screen. Each button is a callback to a different function of what it's supposed to do. So that's why it's called a callback. It's a computer science term. So we hook that in with this fish callback. We're going to add a function called count deletion. And the question is, well, what's the event? Oh, well, the event is this ball delete command. Okay. So again, whenever a ball gets deleted now, this function will get called. Okay. So I can go, let's look at the function. This function now will get called. And this function, when it gets called, will take in a parameter that PFC will pass it, which will be the pointer to the ball that just got deleted. And so that's what I can say. Local BP, ball pointer, is the ball deleted. This is a thing that lets me write stuff to the screen. I.out. And so I build up a string in here. I'm going to say ball, there's a string, plus this is going to give me the ID of the ball. And I'm turned it into a string, so it's going to say ball 6 and then has been deleted. So I'm going to print that to the screen every time a ball gets deleted. And then I'm going to sum it up. I'm going to keep on summing up my count by 1, keep on incrementing it by 1, right? So when I restore the tight pack and I get to here, I'm going to print out the value of my count. And notice it's going to be 0. This is the result. Then I'm just going to issue the ball delete command. PFC doesn't care why the ball got deleted. It just cares that a ball's getting deleted. So notice I'm going to delete balls. Which ones? Oh, I'm going to delete the balls in the range with IDs between 10 and 12. So that means that function should be getting called 3 times, so that now when I print out my count, it should be 3. And so notice 0, my count again is 3. And notice it did get called 3 times, because every time it gets called, it's printing out this string. So there you go, ball 10, ball 11, ball 12. Okay. And that's here, respond to event. So I say respond to event. Oh, wait, I'm still stuck in this continue thing. There, we're done with that. Restore the tight pack. System view, balls. And a few of them got deleted, 10, 11, and 12. And you can see here, just like I went through. Got there. So why? It's still hooked in as a fish call. So I could say ball delete 1 through 4. Ball delete range ID 1 through 4. Sorry. Boom. There, ball delete. Ball 1, 2, 3, and 4 has been deleted. There's some gone, right? Okay. So differently. And these type of events are things like a ball got created, a ball got deleted, a contact got created, a contact got deleted. You know, again, you might be storing information with these things. You might want to be keeping track of this stuff, right? Okay. This is the very powerful thing. We can set it up so that during a time step, during a cycle, as we call it, and we talked about this before, right? This is one cycle. These are the things that happen in PFC. During some portion of this, you can say, oh, at this point right here, just before the force displacement law, I want you to call my function because I'm going to do something. Okay. So this is the way we do this. Basically, these are the different things that happen during a time step. And so each one is labeled with an integer, with a floating point number going from -10 to 80. And so what you do is you say, I want to insert my function to get called at some point during this process. So if you do it at 11, that's the point. It's going to be after the equations of motion, but before body coupling between processes happens, right? So here in the cycle, I've put red by this is the equations of motion, which here I'm calling law of motion. And then eventually it does the force displacement law. Okay, so those are cycle points 10 and 40. Why do we want to do this? This is because PFC, now what I can say is any algorithm that you can describe of things that should be done with particles and contacts, you can implement yourself in PFC. So for example, there was that hydraulic fracturing poroelasticity example. Remember, we had a packed assembly of discs, and then we made a pipe network that was connected to that. And the pipe network was storing pressures and volumes, and it was basically taking its pressures and applying them to the balls that are around it, right? So what we can, that's is how we do this. We basically go at the right point in here. We say every time PFC cycles, at some point it calls my function, which is basically update the pipe network and apply the forces. And so once I hook this in, then my solution procedure is different, right? So I'm modifying the solution procedure. So let's do this. Let's do the example is here. So the hokey example I came up with is during the solution procedure, just before the equation of motion, I want to call my function. And what that function is going to do, see this guy in the middle? It's going to go and it's going to expand that by a factor of 1.1. So it's going to increase its radius by 1.1. Okay. And so how am I going to do that? So I'm creating a function, and this is going to, it turns out that this guy is ball number 117. So load us up here. Here's a global variable called the current radius of ball 117 is equal to, here we go, ball dot radius, which ball? Oh, ball dot find 117. That's the ID you put in. So this returns the pointer to ball 117. And that is used as a parameter to return the radius of that guy. And I'm storing that as a global variable. Okay. Then every time this function gets called, what does it do? It takes that global variable and it multiplies it by 1.1. And then what it does is it just goes and say, oh, here's the new radius, ball attribute radius of that new value. And notice I'm only doing it, the command, for ball number 117. Okay. So this function gets hooked into the solution procedure with this command, fish callback add. Oh, add which function? Expand. And now this is the point in the cycle sequence at which to call the function. So again, I want 9, so it's going to call it just before the equations of motion. And then you can also tell it, you don't necessarily have to do it every single time step. This is saying only do it every 750 time steps, do it. Okay, so now it's hooked in. Now I can say pause. Now I'm going to say cycle 6000. So during the cycle of 6000, I don't know, it's going to call it like 8 times or something, 7 times. Then I'm going to pause again. Then I'm going to show, oh, okay, well, I can also remove that thing from the list. So it's no longer doing it. And then I can cycle some more and the radius should not change. So let's see if this works. Call during cycling. Again, I restore the tight pack. I define the function and I hook it in and I pause. So let's look at that. So 117, I'm not sure which one. It's somewhere near the middle. Oh, there it is. I nailed it. 117. It's this guy right here. Okay. So now every 750 steps, that guy's going to get made bigger. So watch this guy. Here we go. Oh, and I want to show the force chains. Got bigger, got bigger, got called again, it got bigger. Okay, and I'm cycling 6,000. Got bigger still. One more time, I think. Got bigger still. Got bigger still. Now I'm paused. Now I'm sitting out here. Paused. Now I'm going to remove it from the list. So therefore I can cycle more and it won't be doing that anymore, right? So now if I remove it from the list of callbacks, it's not changing anymore. I'm cycling 2,000. It's not getting called anymore. And then just to see what that radius is, it's 0.192. Because that was a global variable and that's what kept on getting incremented. Okay. Okay, respond to event. Let's close that one. Parameter study. Let's close that one. Call during cycling, right? So, we could expand it bigger just for the fun of it. Let's look at this one. Continue. Now it's expanding even more each time. Bigger factor. All right, this is kind of cool. Whoa, look out. Look at those high contact forces. Now if I continue and just cycle, everything readjusts. We go on with life. All right. There we go. Okay. Modify the solution procedure. Let's talk about, there's these built-in fish functions. So there you go, ball.density. And of course, these are all in the manual. Ball.density, and here's what it's going to look like on that manual page. It's going to look like this. What does this mean? There's two things here. This means that you can see the equal sign. If you use it on the right-hand side of an equal sign, it will return to you the density. And this is going to be, that's what it's going to return because it's on the right-hand side of the equal sign. If you put it on the left-hand side of the equal sign, it's going to set the ball density equal to whatever this value is. So you could click on this and it's going to tell you, oh, that's a floating point number. So if you say ball density equals 26, it'll set it. Otherwise, if you just say my variable equals ball density, that my variable will then be equal to whatever it currently is. Okay, and it's telling you this, right? Here's what it returns. Here's what it accepts. Here's the argument. The argument to the function is the pointer to the particular ball you're interested in. Okay. Here's another one. Ball.mass. Notice there's only one thing here. What this is saying is that I can get the value of mass, but I can't set it. Why do you think I can't set the mass of a ball? Because the mass is based on the density. And so that's based on the radius. And so this is how we decided to do it in PFC. So therefore, we don't allow you to change the mass because then this would be weird. Okay. So that's the basic idea. Every function, it either allows you to only get or it allows you to also set. Okay. Now, every programming language has ways of looping. Okay. So there's 4 different ways of looping here. Okay. You can do this loop and loop. It's called the index loop. This is the one we talked about before. If you run this, I is going to be inside the loop is going to be 1, then it's going to be 2, then it's going to be 3. So I'm going to print that out. I equals whatever this is. I equals 1, I equals 2. So if I run this, it'll produce as output this. Okay, so that's called an index loop. It's looping over a number of integers, A through B. There's also a while construct. So this is going to say loop while the variable I is less than or equal to 3, do something. And here again, I'm going to write I equals blah. And then inside the loop, I'm going to increment I. I'm going to start off with I equal to 1. I'm going to check, are you less than 3? Going to increment you, go back. Now I is 2. While I is less than or equal to 3. It is. Do it again. I equals to 3. Less than or equal to 3. Yes, do it again. Now I equals 4. Oh, it's not, this is no longer true. It's not less than 3. So I'm done. And I go on to the next line. Okay. So we've got index loop, we got while loop. And then we also got this more sophisticated one, which you don't need to worry about. This is a C++ construct. It's a more sophisticated way of looping. This is creating a local variable called I, and there's these commas here. It's setting it equal to 1. It's checking, are you less than 3? And then at the end of the loop, it's doing whatever you have here. So it's incrementing it by 1. And so you run this, it's going to give you 1, 2, 3. Okay. And then the last one is this for each. You can visit things. So you can, again, here you go. For each ball that's in the ball list, do something. So this will say visiting ball, da 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 da, right? And you can also do loop for each wall in the system. You can do loop for each contact in the system, stuff like that. Okay. Fish variables, as I said, are dynamically typed. So for example, and these are all these different data types. This is from the manual. Okay, let's just go over them here. So I could say at some point, I could say my var equals the string hello. So now my variable is a string. Then I can go on and say, oh no, my variable is this. Oh, suddenly it's a floating point number. Or I can later on say this. Oh, now it's an integer. Now I get even more fancy. Oh, what's this? Well, this is executing the ball find function, which takes the ID of the ball and returns a pointer to it. So now suddenly my variable is a pointer. A pointer actually is a computer science term that refers to the address, the internal memory address of where the data for that thing is. We call that a pointer because it points to that information. I do this. This is a 2D vector. So now it's actually 2 floating point numbers. This would be a 3D vector. I'm giving it 3 things, okay? And you get the components of the vector either by saying 1, 2, or 3, or by using this construct of the arrow, and you say X, Y, Z, okay? We also have matrix, so a variable. So this is going to be a 2 by 2 matrix of floating point numbers. And this is actually a 2 by 3 matrix. 1, 2, 3, 4, 5, 6. This is wrong. It's a 2 by 3 matrix. We also have a tensor type. So this is actually a symmetric tensor. You typically would use this to store stresses or strains. We have an array. An array is a computer science concept that basically lets you store the array could be my hats, and then you could have 16 hats. So then you would say my hat 1, my hat 2, my hat 3. Okay. Now the array is, and this is a 2-dimensional array. So you could index this by 2 diff. So this is, there are 12 things in here. It's a 3 by 4. It's an array. Each element of the array, it doesn't have to be a floating point number. It can be any fish variable. So inside that array, you could have a string and you could have an integer and all kinds of different things. Okay. And here's how you address that. So my variable 1, 2 gives you element number 1, 2, whatever that is. Okay. This is the list. Okay. And so this is a list. Again, it's a list of what? Of fish variables. Okay, so this is a list that's getting created. And the first element of the list is an integer. The next element is a string, and the next element is an integer. Okay. So if you want to access the second element, you say myvar2. Okay. And if you want to add to the list, you would say, let's say we want to add the string Tom to the end of the list. Here's what you do. So the my variable gets updated. It's equal to what? There's a function, list append. Append it to my variable. What are you appending? The string Tom. So at this point, the list should have 4 elements. So there we go. My variable is the first one, and then we append it, and now we can say, fish list the contents of my var. And when we do that, there you go. It's a list indexed by 1, 2, 3, 4. type, integer string, integer string. And so we have 3 donuts for Tom. Okay. So fish is insanely powerful because it has these dynamically typed things. And because these lists can be made up of any sorts of fish variables. Okay. We do a lot of things when we're writing code with lists. Okay. Okay. Last thing. There is this viewer there. It says fish global symbols. So if we, for example, ran this thing, at this point, we've created 3 global variables. And so the first one is a list. This is that same list we did before that we used for the densities. And say we created this one, and then we created this one, it's a vector, and this one is a string. So notice, and then we did this too, this function. So after we ran this data file in the memory space of PFC, there'd be a variable called myDense, which is a list of size 3. Variable called myPoint, called myString, myWeight, and it's telling you the type of the variable. And then this run cases, it's a function, F1, function with 1 argument. That's what that means. So when you're doing things, it's also sometimes helpful to just be able to look at this viewer of the fish symbols. Just show you that. So what's this one called? Oh, I don't have an example of this, but we can just look at this for example. Parameter study there. Remember when we ran this parameter study, it got the initial state. Let's just look at this. It increased the density. It increased the density again. It increased the density again. And we're done. And as we did that, like for example, there should be a global fish variable called myDense. So we look over here, fish global symbol, myDense, size 3, it's a list, right? Run cases, weight balls. Those are the only fish things we created thus far, okay? So that's the fish viewer. And so now let's go fishing.